G'day guys, 1 hour hero here with another electrical video. Today's topic will be losses through electrical systems. More specifically, copper losses. This just proves one thing, that I am the hottest guy in this room. Okay, so the story begins. I've got this car. It's an old Falcon. Now this car, it's quite old. The heater began to stop working. It's a $5 part to fix, but it's inside the whole dash. You have to take the dash out. It's a whole day's work, $800 if you get the mechanic to do it. But I thought, stuff it. You know what? I'll splurge a bit on this $12 heater on eBay. How good's that? I'm gonna be nice and warm in the morning. Oh, it's gonna be brilliant, yeah? Look at this thing. It's just quality. Or is it? I'm gonna boot this baby up. Got this pretty cool looking power supply. We're gonna have a play with this. I'm gonna show you some copper losses. So what happened? I was driving to work in the morning the first time that I used it, and I felt something warm against my leg, which is pretty normal, yeah? It is a heater. But it wasn't the air from the heater hitting my leg, it was the cable. I bought a heater so I could heat the air, not heat a cable. Take voltage off car. Take one. I need to take a voltage reading of my car without the motor running and one with the motor running. I want to see the voltage that my car is outputting with the alternator charging the battery. Let's go. How does that look?
Maybe you should put a light outside. Look at the crappy lights I have to live with, living with an electrician.
You need to hold that.
Doing the camera, mate.
12.75 volts DC without the car running. I'm going to start the car. Let's see how high it goes.
Should I get your rego in?
No. 14.5 volts DC. Interesting. My heater was only rated to 12 volts and I'm putting 14.5 volts in. No wonder it's getting hot on these cables. So I've got this installation all set up, just like I would in the car. I want to replicate what was happening. Here's my voltmeter on DC. Here's my current meter. It's wired in series with the load, always series with the load. You put an amp meter parallel to load, I will kick you. Won't you, I'll just kick you. We know that 12 volts is on our battery, right? But our alternator actually puts out something like 13.5 to 14 volts just to charge our battery, yeah? It's got to put a higher voltage than what it's actually rated at, just to get some charge into that battery. I'm gonna put it on. We'll start low. Here we go. I'm gonna turn the fan on. This is not the heater, this is just the fan. I'm sure if you can hear that. We've got 0.2 amp at 7 volts, but that's not what we run. If you get a voltmeter and go to your car battery and read the voltage over the battery whilst the car is on, you will see that it's actually around 14, maybe 14.5 depending on the alternator. 14.5 volts. So let's go to that. 14.4 volts, yeah, 0.4 of an amp. Nothing's blowing pretty hard. Let's have a look on our thermal camera. Oh, there's me. Oh yeah, hello. Okay, so I've got it pointed at it. There actually is no red hot spots on the fan itself. The red line horizontal is actually just the bench. It might be a bit of residual heat from the day. Let's crank it. As soon as I put it on the heat setting, the voltage, we get a volt drop with this certain power supply. Let's go to 12 volts, why not? There is 12 volts right there. And look at that, we're pulling 10 amps. 10 amps, we're gonna blow the fuse if we keep going. So you can imagine if we put this on our car battery, we're actually gonna get quite a high current flowing through this. That's 9 amps already on 11 volts. So let's just see what it's doing. This should be a big difference now. This is a heater after all. This section here is where the heat is coming out. That's the heating element. You'll see that, look at that, right there. That's hot. We're talking 60 degrees Celsius or so. 65, 60, so cool. What about our cables? Wow, look at that. Easily see the cables and the current flowing through the cable. As you can see, our cable, they're glowing red hot, just as hot, almost as hot as the element. Can you see this? It's nuts. Some electron flow in that baby. That's only at 9 amps and at 11.5 volts. So let's do it. Let's crank this up to 14 volts. This meter, only good for 10 amps. What I've done, I've got 2 amp meters in parallel. They are for, I can pull more than 10 amps even though they only have a 10 amp fuse, because I'm sharing the fuse load over 2 amp meters. So I might be pulling 13, 14, 15 amps, and that's cool. You'll just see that maybe I'll have 7 amps on one and 7 amps on the other. Therefore, I'm under that threshold of 10 amps. Very rare you'll have to do something like this, but I just thought I'd show you. It's really interesting. All right, so let's turn this baby up. Watch these amp meters go nuts. Nuts, tire nuts. So you picture me in the morning, turn my car on, it's at 13.5 volts. Watch the current. Look at it. I'm maxed out on my volts. Can't get any more. 13.2 volts at 6.2 amps, 6.45 amps. So that's a total of about 13 amps through this little pissy flexible cable. This is red hot in my hand. That's what I was feeling in the morning. And yet I'm only at 13 volts. Do you know what? I think it would have even got hotter. 14.5 volts. But my power supply can't really give that much current. Interesting though, isn't it? To say that that was what's going on. One of the biggest places that we can get these copper losses that I've noticed in the domestic situation anyway, is a vacuum cleaner. This thing pulls almost 2,000 watts. This cable, I'm not going to say it's quite small just looking at it. Pulling 2,000 watts through a small cable is going to generate a lot of heat due to I squared R. That heat in the cable right now. I wonder if it registers on our thermal camera. Now sometimes you see when you buy a new appliance, you say do not run if the cable is all wound up. Like this, for example, you must unwind the cable before turning on that appliance. It's because I squared R, as you pull current through a resistant cable, we create heat. Now if we bundled up our cables, we're going to get a hot spot. This is not good, yeah? This is why they ask you to unwind those cables first. Look at that, a hot spot now. If they can't breathe, we've got the potential to create a fire.
In a circuit, due to this squared here for the current, we double the current, we actually times the power loss by 4. I'll show you this right now. I've used 1 as my constant, which is my resistance. That won't change, I will change my current in this circumstance.
Got 100 watts
of power loss if this was a cable with 1 ohm. Now,
I'm going to double that current.
20 amps.
I've now lost 400 watts in that same lead. All I've done is double that current. Here I've just done a little drawing of a circuit using figures that I've taken from the example when I was using the power supply. I've just actually gone and hooked up that heater again on my car. I didn't take footage of it. I actually got a volts drop from this point, the start of the cable, where the connection of the cable is, to this point, which is just to the start of the element, and I had a volt drop of 0.25 volts or 250 millivolts. If you think about it, I've got the same size cable. I'm just going to assume that I had the same volt drop from here to here, 2.5 volts, with a total volt drop 0.5 volts. The next thing to say is that now my heating element, which is this, is not getting all of this voltage. We've actually got this total voltage, take 0.5 volt, and that is what the volt drop over our heating element would be, which is 12.57 volts. So I've got 0.5 of a volt drop over these two cables. Let's do a bit of Ohm's law. I don't have a pure resistance as my meter is not sensitive enough to go down below 0.1 of an ohm, but we can figure it out using Ohm's law. R equals V divided by I, and we've got the volt drop in those cables, 0.5 of a volt, divided by the current total flowing through this circuit, which is a series circuit, 12.81 amps. And that leaves us with 6.4. And that leaves us with about 0.4 ohm in these cables.
So power loss is equal to I squared times by R, which is equal to 12.81 amps flowing through my series circuit, squared times by 0.04, which is the resistance of the cable, and that will equal 6.564 watts. Just my cables alone are using 6.564 watts, and that energy is dissipated via heat.
Interesting. How cool is that? And how dangerous is that? Those conductors are creating a heat, and they're covered in this plastic insulation which can melt. And it's this exponential effect with this squared. The cable felt fine when I was only pulling a few amps, and then I go and add a few more amps, and next minute the cable's red hot. It's an exponential graph. Shit gets crazy. And that has been my little introduction to copper losses and I squared R losses. Obviously a very quick explanation, but anyway, if you liked it, give me a like and make sure you subscribe. I'd really like the subscribes. Cheers guys.